Hello, my name is Kevin-san. In this video, we'll be talking about sparsification of directed graphs via cut balance. This is joint work with Ruoxu Cheng, and Debmalya Panigrahi. The purpose of graph sparsification is to approximate a graph G using a sparser graph H. That is, H should contain fewer edges than G. One reason for this is that storing H would require less space than storing G. And if H satisfies certain properties, then we can run an algorithm on H rather than on G. And since H has fewer edges, the algorithm would run faster. A sparsifier is a weighted subgraph. So if our input graph looks like this, then a sparsifier looks like this. One property we often want to preserve is the cut values. So for any cut in G, the value of that cut in H should be approximately equal to the value of the cut in G. More specifically, if we're given a graph G on n vertices and some parameter epsilon, and let delta S denote the number or weight of edges crossing S, then our goal is to construct a sparse subgraph H on V such that, with high probability, all of the cuts simultaneously are preserved. That is, delta S in H, the weight of edges in H crossing S, is up to a 1 plus minus epsilon factor, the weight of the same set of edges crossing in G. In addition to sparsifiers, we will also be considering sketches. So recall that a sparsifier is a weighted subgraph of the original graph. Here we relax this condition to be any arbitrary data structure, which we'll call a sketch. So now our goal is to construct a data structure, and we'd also need to specify a recovery function such that with high probability for any cut, we can recover the value of that cut in the original graph up to a 1 plus minus epsilon factor. So in this case, if our graph looks like this, we would specify how to construct the data structure using the input graph. And then upon a query, which is simply a subset of vertices, we should be able to determine using the recovery function the value of that cut in the original graph, again up to a 1 plus minus epsilon factor. But if we go back to sparsifier results for a second, for undirected graphs, one major approach is random sampling. Here we sample each edge E with probability PE, roughly log n over lambda E epsilon squared, where lambda E is an edge parameter. Bengzer and Karger showed that setting lambda E to be a quantity known as the edge strength would yield a valid sparsifier with roughly n over epsilon squared edges. Spielman and Srivastava showed that lambda E could also be the effective conductance. And Fung and others showed that other edge parameters also work, such as connectivity and NI index. All of these parameters yield valid sparsifiers under the random sampling regime. In 2009, Batson and others gave a deterministic algorithm and also removed the log factors. And then more recently, Carlson and others showed that n over epsilon squared edges are required, so in some sense this question is resolved for undirected graphs. Now notice the dependence on epsilon squared. If epsilon is less than 1 over square root n, then a sparsifier would require omega n squared edges, which is no better than simply storing the entire graph. In light of the matching lower bounds, we also consider a relaxed guarantee known as the for each guarantee. In this situation, we're still constructing a sketch and recovery function, but now the guarantee is that for each cut, the value is preserved with high probability. In contrast, we previously guaranteed that with high probability, all of the cuts are simultaneously preserved. This notion was introduced by Andoni and others in 2016, and they gave a sketch of size n over epsilon. Later, Chu and others showed how to construct a similarly sized graph rather than a sketch. Notice that the dependence on 1 over epsilon has decreased from 1 over epsilon squared to 1 over epsilon. Andoni and others also showed a nearly matching lower bound of n over epsilon for the for each guarantee. So as mentioned in the title of this talk, we'll be considering sparsification of directed graphs. And we'll start by considering Eulerian graphs, which are, in some sense, the least directed kind of directed graphs. Because if we look at any cut, the number of edges leaving the cut and the number of edges entering the cut are always the same. So we can actually, to sparsify an Eulerian graph, we can actually ignore the edge directions because every cut is balanced in this sense. The ratio of the number of edges leaving and the number of edges entering, in this case it's 2 over 2, and for any Eulerian graph in any cut in the graph, it's 1. In contrast, let's consider a very directed graph, which is the complete bipartite graph. So we have all of the edges go from left to right, And let's consider an edge UV. And so for any edge, we can consider the cut consisting of U on the left and then all the vertices on the right, except for V. Notice that the only edge leaving this cut is UV, so this cut has value 1. In order to preserve the cut value, we would have to store this edge in our sparsifier. And if we have to store every edge in the sparsifier, this defeats the purpose of sparsification. But in some sense, this graph is highly directed, because if we simply consider the balance ratio, as we saw before, for any cut, the number of edges leaving to the number of edges incoming, many cuts have infinite balance ratio. So if we consider any single vertex on the left, the number of edges leaving is, in this case, 4, and the number of edges entering is 0. So the ratio would be infinity. So a natural question to ask is there a way we can take this balance parameter and use it to construct graph sparsification algorithms for directed graphs that degrade with the balance of the graph? So now let's formalize the notion of balance in directed graphs. So if we're considering a strongly connected directed graph, we say it's beta balanced if the value of edges leaving the cut is at most the beta times the value of edges coming into the cut. So in this picture, the red edges are leaving and the blue edges are coming in, and the value of the red edges, the total capacity, the total weight, is at most beta times the value of the edges coming in. Notice that if a graph is unweighted, then this beta parameter is always between 1 and n squared. And so we say it's beta balanced if beta is the minimum over all possible betas, such that this inequality holds for all cuts in the graph. This notion of balance was introduced by NA and others in 2016. One of the problems they considered was single source oblivious routing. So for beta balanced graphs, they gave an algorithm whose competitive ratio scaled with beta times log cubed n. And as we can see, as beta varies from 1 to n squared, this gives us an interpolation between the best competitive ratio for undirected graphs and for general directed graphs. Similarly, for approximate maximum flow, they gave an algorithm whose running time scales with m times beta squared. And again, as beta varies, this gives us a nice interpolation between undirected graphs and directed graphs. We considered for all sparsification of directed graphs. So recall that for undirected graphs, we can sample n over epsilon squared edges. And so the question is, what about beta balanced graphs? So a natural algorithm is to simply ignore the edge orientations and then boost the sampling rate by a factor of beta. So Ikeda and Tanigawa showed that this procedure does return a for all sparsifier, which has beta n over epsilon squared edges. So a natural question to ask now is this dependence on beta necessary? And we show that the linear dependence on beta is indeed tight. In fact, we show that any for all sketch, so not just sparsifier, must output at least beta n over epsilon bits. The dependence on epsilon is not tight, but our main contribution here is to show that this linear dependence on beta is tight. Ikeda and Tanigawa showed that beta n over epsilon squared edges are sufficient to sparsify any beta balanced graph. But what about directed graphs that aren't uniformly beta balanced, in the sense that in the graph, maybe many of the cuts are actually very balanced and only a few are unbalanced. So many of the cuts are alpha balanced where alpha is less than beta. So we generalize their result to apply to any directed graph. The input to our algorithm is a directed graph and a parameter beta. And it returns a subgraph containing beta n over epsilon squared edges, and it preserves the value of all the beta balanced cuts up to a factor of 1 plus minus epsilon. So in particular, if every cut is beta balanced, then we recover the result of Ikeda and Tanigawa. Moreover, the preservation factor improves for cuts that are more balanced. So if a cut is alpha balanced where alpha is less than beta, the approximation factor is better than 1 plus minus epsilon. Using this result, we can actually produce a short proof of a maximum flow algorithm. This was given by Karger and Levine in 2002, runs in m plus nv time, where v is the value of the maximum flow. Their overall approach is sample from the residual network to find an augmenting path, and by applying our result to the residual network, we can prove that an augmenting path indeed exists. So now we turn our attention to the for each sketch. So recall that in this guarantee, we with high probability each cut should be preserved rather than with high probability all the cuts are simultaneously preserved. So for undirected for each sketch, Andoni and others gave a data structure that has n over epsilon bits. We show that a linear dependence, so unlike the sparsifier situation, when we move to directed graphs, so beta balanced graphs, a linear dependence on beta is not necessary. So for a beta balanced graphs, we give a sketch that has square root beta n over epsilon bits, and we show that this dependence is tight. In particular, any for each sketch must output omega root beta n over root epsilon bits. Again, the dependence on epsilon is not tight, but we do show that this square root dependence on beta is tight. So a summary of results. So for each sketches, we show that we give an upper bound of root beta n over epsilon bits and a matching lower bound to show that dependence on beta is tight. For all sparsifiers, we show that for any directed graphs, we can sparsify in the sense that we can preserve the beta balance cuts up to a 1 plus minus epsilon factor using a linear dependence on beta, and then we also show that this linear dependence of beta is necessary. We'll start the next part of the talk by sketching the idea for our for each sketch. The outline for this part of the talk is, firstly, if we're given a beta balanced graph G, how do we construct the sketch? And then we should analyze how large is this sketch. Then we need to specify the recovery algorithm. So given the sketch and a query, how do we estimate the weight of this query in the original graph? And then how do we prove that our estimate is approximately equal to the original weight of the cut in the graph? So the overview of the sketching algorithm is to deterministically store and remove all edges belonging to sparse cuts, which we will define later, ignoring directions. And then at every vertex, we take a sample of incident remaining edges in both directions. This sample is done uniformly at random in both directions. So in this picture, the blue edges represent the sparse edges. These are stored deterministically, as we'll see. And then the red edges represent sampled edges in both directions. To be more specific, we say a cut is sparse, a cut S is lambda sparse, if the total number of edges, so ignoring direction, is at most lambda times the minimum size of the two sides of the cut. So in our case, we set alpha and lambda as root beta over epsilon. While there exists a lambda sparse cut, we remove and store all of these edges of the cuts in both directions. And then we store the remaining in and out degree of every vertex. This can be done in a linear space. And then for each vertex, we sample with replacement and store alpha incoming and outgoing edges. So again, with the picture, the blue edges are stored, found and removed deterministically, and then we store the degrees, and then we sample the red edges, which is alpha incoming and outgoing edges with replacement from each vertex. So first we analyze the size of this sketch. So recall that there's the first step was to remove lambda sparse edges. So recall a lambda sparse edge means the total number of edges, so ignoring direction, is at most lambda times the smaller side, which we'll assume is S. And we claim that this is lambda and log n, the total number of lambda sparse edges. So whenever we remove a lambda sparse cut, let's charge the edges that we remove to the smaller side. So in particular, every vertex gets charged at most lambda times because the number of edges is at most lambda times S per cut. And a vertex can only appear in the smaller side of a cut log n times, since the cut side it would appear in would half every time. And so overall, the total number of charges would be lambda and log n, which is the number of edges that we're storing. To store the remaining degree values, this is simply a log n for each of the n vertices, so this is n log n. And then we sample 2 alpha edges incident to each vertex. Again, it's actually at most this because it's with replacement, and this requires alpha and log n space. So the total is lambda plus alpha times n, which is up to log factors. And recall that lambda and alpha are both root beta over epsilon, so this gives us our desired size of the sketch. The recovery algorithm for our sketch is fairly natural. So given a query S, subset of vertices, we can compute the contribution of the lambda sparse edges exactly because these are stored deterministically. And then we just add the normalized contribution of sampled edges from each vertex in S. So again, if our cut looks like this, after removing the edges in lambda sparse cuts, we are left with these what we'll call dense components. And the blue edges we can compute exactly, and then for each component we sum across the normalized contribution of edges crossing the cut. So again, we can compute the total number of lambda sparse edges that cross the query exactly because we've stored them deterministically. And then we consider the dense components, the remaining components, and a vertex u that is in a dense component T and on the side, the cut side of S. And we scale the contribution of U to S, to the value of S, by this factor of delta UT, which is the number of edges after removing the sparse edges, the number of edges within the component T leaving U, divided by alpha. This gives us the right normalization factor since we sampled alpha outgoing edges uniformly at random incident to U. So notice that this estimate is more accurate if many sampled edges are crossing the cut. So in particular, we hope that the intersection of S and T is small compared to the intersection of S bar and T. If this is not the case, if the other side is smaller, then we actually should estimate the number of edges entering T and S bar rather than the edges leaving T and S. This will give us a more accurate sample, and this is why we also sampled alpha outgoing and incoming edges in case the smaller side of the component is actually outside of the cut, is on the opposite side of the cut. This is also perhaps the main reason why this isn't a weighted subgraph, in the sense that we cannot simply look at the value in the value of a cut in a subgraph, because sometimes we have to look at the value of the edges entering a cut rather, so we'd have to switch sides for certain components. Now we give an overview of the proof of why our estimator is accurate with high probability. We'll start off with Chebyshev's inequality, which says that if a random variable x has expectation mu and variance sigma squared, then the probability that the difference between x and mu is more than k times sigma is at most 1 over k squared. In our case, x is our estimate, which has a deterministic and randomized part. The edges in the lambda sparse cuts are deterministic and the sampled edges are randomized. And from our estimator, we can show that mu, the expectation of x, is the value of the cut in the graph. In our proof, we show that the standard deviation of our estimate is roughly epsilon times its target. So this implies by Chebyshev's that the probability our estimator fails is at most a constant. The main challenge is that for undirected graphs, we can calculate this standard deviation component-wise. That is, after removing the edges belonging to sparse cuts, we can look at each of the dense remaining components, calculate the standard deviation within the component, and sum across all the dense components to bound the overall variance. But for directed graphs, these components are not necessarily balanced, so we wouldn't be able to apply a local analysis of the standard deviation within each dense component. But we show that despite this, we can bound the overall variance by analyzing all of the components at once using a more global analysis, and then applying beta balancedness at the end. In order to reduce the error probability, if we already have that it's at most a small constant, then we do a standard trick of constructing log n copies of the sketch. When we receive a query, our final result is the median value returned by these copies. So that was the overview for an upper bound for each sketch of beta balanced graphs, showing that a square root beta dependence over the undirected case is sufficient. Now we show that this dependence is necessary. So the proof idea is from communication complexity. So suppose Alice has a string S, and she encodes it into a graph and then sends the sketch of this graph to Bob. Bob, upon receiving the sketch, the sketch enables him to deduce each bit with probability 2/3. And so more specifically, if the length of S is n squared, the graph will be bipartite, and beta is roughly n squared. Because Bob is able, so given the sketch, Bob is able to deduce each bit of S with probability 2/3, the sketch needs to encode almost the entire string S, and from a standard result in information theory, we can conclude that the size of the sketch must be at roughly the length of S, which, since it's n squared and beta is n squared, is omega root beta n. The epsilon dependence is similar, but we won't go into the details. Now we'll move on to our results for 4-all sparsifiers, starting with a quick note about our upper bound. Our algorithm is the sampling algorithm stated earlier, with sampling probabilities boosted by a factor of beta. A more refined analysis shows that we can apply this to any directed graph to preserve the value of all beta balanced cuts. Again, one consequence is a short proof of the maximum flow algorithm of Karger and Levine, but we will not go into the details. Finally, we'll look at our lower bound for 4-all sparsification. To obtain our upper bound, we simply boosted the sampling probabilities by a factor of beta, so it is natural to ask if there is a more sophisticated approach that would result in a smaller sparsifier. But our lower bound shows that this linear dependence on beta is indeed necessary. In fact, our lower bound applies to any 4-all sketch, not just any 4-all sparsifier. Again, we will assume that epsilon is a constant because this simplifies the proofs while preserving the main ideas. So we want to show that any 4-all sparsifier for beta balanced graphs has size omega beta n. Our strategy will be to construct a large family of graphs F on 2n vertices, such that every graph in F will be beta balanced, where beta is 8n, and a single sparsifier approximates only a small number of graphs in F. So if F is represented by the box, and the yellow circles represent sparsifiers, then any sparsification algorithm will show that when run on F must output 2 to the n squared different sparsifiers, and in order to output this many different sparsifiers, the large sparsifier must contain at least n squared, which is, in this case, omega beta n bits. To give a bit more detail, every graph in F will have 2n vertices. It will be bipartite with n vertices on the left and n vertices on the right. The edges from the left to right form a fixed matching. The edges from the right to left are arbitrary, but the graph must be beta balanced for beta equals 8n. So as we can see, the edges from the left to right are fixed, while the from right to left can be arbitrary. We proved two lemmas. So one says that F is large, at least 2 to the n squared over 2 graphs are in F, and a sparsifier, a 1 plus minus epsilon sparsifier, covers at most 2 to the n squared over 4 graphs in F. So putting these two lemmas together actually gives us our result. Sparsifying F requires at least 2 to the n squared over 2 over 2 to the n squared over 4 different sparsifiers, and that's 2 to the n squared over 4. So in order to output this many sparsifiers, as we said before, the algorithm needs to output at least beta n bits, because beta equals 8n. So we conclude with a summary of our results. For each sketches, we give an algorithm that produces a sketch that preserves each cut with high probability, and this sketch has size square root beta n over epsilon. And then we also give a lower bound showing that this square root beta dependence is necessary. For 4-all sparsifiers, we show that for any directed graph and parameter beta, we can sample beta n over epsilon squared edges to preserve all beta balanced cuts. The cuts that are more than beta balanced, that is, they have balance factor smaller than beta, have better preservation factor. And then we also show that this linear dependence on beta is necessary, and this also holds for sketches. Thanks.